So the second class of reaction that we're going to look at in section 4.2 is what is known as acid-base reactions. So to begin looking at acid-base reactions, we should define what we mean by an acid and a base. And an acid can be defined as a substance that produces hydrogen ions when dissolved in water. So we have a substance, I'm just going to call it HX, and when we dissolve it in water, it separates out into an anion and one or more hydrogen ions. A base can be defined as a substance that produces the hydroxide ion when it's dissolved in water. A good example of this are soluble metal hydroxides. When these guys dissolve in water, because they're ionic species, they dissociate into hydroxide ions and a cation. Some species, such as metal oxides that are soluble, will react with water and form hydroxide ions in that fashion. So when magnesium oxide is added to water, it will form magnesium ions, but also hydroxide ions, and so that makes magnesium oxide a base. So the definition of acids and bases that we've given here is what's called the Arrhenius definition of acids and bases. It turns out that there are a couple of other ones, but this one's pretty good for where we're at right now. So it's important to realize that a hydrogen ion is simply a proton, because a hydrogen atom comprises one proton and one electron. There are no neutrons in the nucleus of a hydrogen atom. So when a hydrogen ion forms, the hydrogen atom loses its electron, leaving behind a proton. Now, the proton is the most condensed form of positive charge you can get, and it interacts very strongly with water molecules. So strongly, in fact, that it forms a covalent bond to water molecules, forming what we call the hydronium ion whenever the proton is solvated in water. So it's important to realize that hydrogen ions are always present in water as hydronium ions. Now, frequently people will write H plus AQ, when I guess technically they should write H3O plus AQ, but people understand what's going on and are able to interpret that appropriately. So let's think about the dissolution of a typical acid in water now. So say we have hydrogen chloride, it's a gas, and we bubble it through water. When hydrogen chloride is dissolved in water, a proton gets transferred from the hydrogen chloride molecule to the water molecule, generating a chloride ion and the hydronium ion. So the acid donates a proton to the water. As I mentioned previously, you will see that people will frequently write H plus AQ instead of H3O plus AQ, and they'll assume that you understand that the hydrogen ion will covalently bind to the water molecules present. So the second definition of acids that's useful to keep in mind is what's called the Bronsted-Lowry definition. In the Bronsted-Lowry definition, an acid is what's called a proton donor, and a base is a proton acceptor. So going back to the example that we had before, the hydrogen chloride donates a proton to the water, so that makes it an acid, and the water accepts a proton from the hydrogen chloride, so that makes it a base. So there you go. An acid can be defined as being a proton donor, and a base can be defined as being a proton acceptor. Now, it's important to realize that anything that is an Arrhenius acid is also a Bronsted-Lowry acid, and anything that's an Arrhenius base is also a Bronsted-Lowry base. So we've just kind of expanded our definition to eliminate the need for water to be present. Some Bronsted-Lowry bases, such as ammonia, are a molecular species. That is, they are not ionic compounds like magnesium oxide or sodium hydroxide. And these species form hydroxide ions through a reaction with water. So what we see is our Bronsted-Lowry base, such as ammonia, accepting a proton from water, which functions as the proton donor or the acid. This will generate a cation, and the water gets converted into the hydroxide anion. So you can see it really is a substance that when dissolved in water produces the hydroxide ion, so it's definitely a base, right? A lot of biomolecules are molecular species of this type. That is, they are not ionic compounds. And perhaps the most famous example would be the DNA bases, your A's, C's, T's, and G's. They're called bases because they are all bases and function as proton acceptors. So people will often discuss the strength of an acid or base. And the strength of an acid or base depends upon the extent that they dissociate into ions in aqueous solutions. In particular, an acid or base is defined as being strong if it completely, if the molecules or ionic compound that are present completely dissociate into ions when they are dissolved in water. In the opposite sense, an acid or base is defined as being weak if, when dissolved in water, very little or most of the molecules or the ionic compound remain intact. So it's important to recognize that acid strength and base strength is not related to concentration. It's related to this extent that the compound dissociates into ions when it's dissolved in water. So you will need to learn to recognize strong acids and weak acids on the basis of their formula. So the first thing is you can tell that something is an acid because it has to have at least one proton to donate, and that proton will be written at the beginning of the formula. Now, strong acids are of two types. There's a group of 3, which are sometimes referred to as hydrohalic acids, or also sometimes referred to as binary acids because they've only got 2 atoms present. And these are hydrochloric, hydrobromic, and hydroiodic acid. Those guys are strong. So hydrogen combined with a group 7A element. Note that hydrofluoric acid, HF, where fluorine is also from group 7A, is not a strong acid, so you have to remember that one. The other class of strong acids are these oxygen-containing acids. And you'll notice something interesting about these guys. They all have one or more hydrogens, a second non-metal element, and then one or more oxygens. So kind of like that would be the generic formula, if you will. These are sometimes called oxoacids, and sometimes people will call them oxyacids. You'll see different spelling there, but they mean the same thing. The oxyacids that are strong all have something in common, and that is that they have at least 2 more oxygen atoms than hydrogen atoms. So that's worth taking a note of. So in HNO3, we have 2 more oxygens than hydrogen, so nitric acid is strong. In H2SO4, we have 2 more oxygen atoms than hydrogen atoms, so sulfuric acid is strong. In HClO4, we have 3 more oxygen atoms than hydrogen atoms, so perchloric acid is strong. So we should be able to recognize the binary or hydrohalic acids that are strong. That's kind of a memory task. And using our little rule about the number of oxygens, we should be able to recognize oxyacids that are strong. The common weak acids include hydrofluoric acid, so HF, oxygen-containing acids that don't have enough oxygen to be strong. So a good example would be H3PO4, where we only have 1 more oxygen than hydrogen. It's known as phosphoric acid. And then there's a class of acids which are called carboxylic acids. And they all have an ending COOH in their formulas, so you can recognize them. Carboxylic acids. We're going to learn about those in organic chemistry. Perhaps the most famous of these is acetic acid, which is the acidic component in vinegar. And then something that makes it really, really easy is if it's not strong, it is by default weak. So anything that's not strong is automatically weak. Okay, so really you just need to remember these guys and the rules for identifying strong acids, and then anything else, anything that's not strong is automatically weak. Okay. Strong bases are ionic compounds that contain the hydroxide ion. They're commonly group 1A and group 2A metal hydroxides. Most metal hydroxides are not water soluble. That's why we're limited to group 1A and group 2A if you think about the solubility rules. Typical weak bases are molecular compounds that contain nitrogen, and perhaps the most famous one is ammonia. So NH3. I guess equally as famous would be those DNA bases that we talked about previously. So this section is about acid-base reactions. So now we want to think about what happens when an acid reacts with a base. And it's pretty simple. The acid will produce H+, the base will produce OH-, and so when an acid reacts with a base, the hydrogen ions formed by the acid react with the hydroxide ions formed by the base to make water. So this is a typical molecular equation for an acid-base reaction. In this case, it's quite a simple one. It's the reaction of sodium hydroxide with which is our base, with a solution of hydrochloric acid, HCl. And so what's going to happen is that the acid will dissociate, forming hydrogen ions and chloride ions. The base will dissociate, forming sodium ions and hydroxide ions. And as we mentioned in the opening, the hydroxide ions will combine with the hydrogen ions to make water. And the cation formed by the base will combine with the anion formed by the acid to make an ionic compound. So the reaction of an acid with a base is often summarized by the expression acid plus base equals salt and water. And salt is just is a synonym for ionic compound. So when an acid reacts with a base, we make an ionic compound and water. Now, your job is going to be to figure out how to balance these guys, make sure we have the correct ratio of all of the reactants, the correct number of water molecules that are being formed, and then also to correctly identify the ionic compound. One complication is the ionic compound might be water soluble, and it might form a solid. So often we have to check the solubility rules to get the correct phase label on the ionic compound that forms. So when we write the molecular equation for the reaction between a base and an acid, such as sodium hydroxide and hydrochloric acid, we keep everything in its undissociated form. So the acid is written in its undissociated form, even though we know it dissociates fully in water. The base is written in its undissociated form, even though we know it dissociates completely in water. The ionic compound that is formed is also written in its undissociated form, even though we know that it dissociates into ions when dissolved in water. Of course, water molecules do not dissociate into ions. So something that you might be asked to do is to dissociate those compounds into its component ions that are known to do that. And that gives us the overall ionic equation, just like we had for precipitation reactions. So in this case, we would dissociate the strong acid, hydrochloric acid, into hydrogen ions and chloride ions, the strong base, sodium hydroxide, into sodium ions and hydroxide ions, the water-soluble ionic compound, sodium chloride, into sodium ions and chloride ions, but we would leave intact the covalent compound water because that doesn't dissociate into individual ions when it's dissolved in water. So the rule is any strong acids or strong bases get dissociated into individual ions if we're asked to do that, and any water-soluble aqueous solutions of ionic compounds also get dissociated into ions. Things that don't get dissociated into ions would be weak acids or weak bases, or ionic compounds that are in the solid state. Also, we would not dissociate any covalent compounds that are not acids. So, as I mentioned, when we dissociate those things that dissociate completely into their component ions, we end up with what's referred to as the total ionic equation, or sometimes people call it the overall ionic equation, and it's going to look like this. Now, if you look closely here, you'll see that some ions appear in identical forms on both sides of our arrow. So it isn't an uncommon thing to do to cancel out these what we call spectator ions. And when we do that, this gives us the net ionic equation for our acid-base reaction. So in this case, we would get rid of chloride ions and sodium ions, and we can see really clearly what's going on here. Hydrogen ions are reacting with hydroxide ions to form water molecules. So here's a typical example problem from the book. It says complete and balance the equations for the following acid-base neutralization reactions. If water is used as a solvent, write the reactants and products as aqueous ions. In some cases, there may be more than one correct answer, depending on the amounts of reactants used. Now, I only picked one of these problems out, so we don't have to do a whole bunch of work here. Okay, so let's look at what we've got. We can read the formula magnesium hydroxide and immediately recognize that this is a strong base. Now, it's a solid, so we won't dissociate it. Okay, solids do not exist as dissociated ions. When we look at the formula of what our strong base is being reacted with, we see it starts with hydrogen, ends in AQ, which is a giveaway, it's an acid. And so we're going to ask ourselves, is it a strong acid or a weak acid? Well, because we've got 4 oxygens and only 1 hydrogen, we have 3 more oxygens than hydrogens, we can tell from the formula that this guy is a strong acid and it's in aqueous solution, so we're going to dissociate this guy into hydrogen ions and anions. Okay, so when an acid and a base react, they're going to make 2 things, aren't they? They're going to make water, which is a liquid, and they're going to make an ionic compound. So we better figure out what our ionic compound is. So how we're going to do that is we're going to get our cation and our anion. And what I always like to remember is the anion comes from the acid. So if I take one H plus away from HClO4, take away a 1 plus, that must mean that that anion has a single negative charge. Now, if the anion comes from the acid, the cation must come from the base. And our cation is always written first when we write the base. So what's the charge on the magnesium ion? Well, magnesium's in group 2A, so it's 2 plus. So we can see that these guys don't have equal and opposite charges. So we're going to use crossover rule to get our formula of our ionic compound, and it must be MgClO4 2, and that's going to be dissolved in water. So we're going to make water, and we're going to make MgClO4 2 AQ. It's going to be dissolved in water. There we go. Okay, so now we need to balance this guy. And hopefully immediately you can see that I've got 2 of my anion in my products. So that tells me I'm going to need 2 of my acid, aren't I? I'm going to need 2 of my acid. Okay, so that kind of, that gets us part of the way towards balancing this. But if you're observant, you'll see that we seem to have way too many hydrogen atoms present. And on the left-hand side, we've got 4 hydrogens, and on the right-hand side, we have only 2. So how we're going to fix that is we're going to put a 2 here. And as a general rule, what you'll typically find is the number of hydroxide ions that are reacting will always equal the number of water molecules that you form. Okay, so at this point, it looks like we have our balanced molecular form of our equation, all right? 1 magnesium hydroxide reacts with 2 perchloric acids to give 2 water molecules and 1 magnesium perchlorate. So what we have to do now is dissociate those things that exist as individual ions in aqueous solution. So let's see what that might be. So this is an ionic compound here, but it's a solid. So as mentioned before, we're going to leave it undissociated. This guy is a strong acid, so we will dissociate it. This guy here is a covalent compound. It's not an acid, so we're going to leave it alone. So it's not going to be dissociated. And then this one here, If we look up magnesium perchlorate in our solubility rules, we will find that it is a soluble ionic compound. So this one is going to dissociate into ions. So there we are. So MgOH2 solid plus, and then now we're going to separate this guy out into its ions. 2 hydrogen ions and 2 what we call perchlorate anions. Then we have 2 waters. And finally, a magnesium ion and 2 what we call perchlorate anions. And everything looks balanced. A little bit cramped on the space there, but this is why I do encourage you to write things out on a nice big piece of paper. All right, we don't need to cancel ions out in this case to get the net ionic equation. So it looks like we're done. Let's check the answer. I'm going to leave that intact. I don't know why they left that guy intact. It's incorrect. I'm going to dissociate that, and leave that intact. Okay, this really should have been split out into the component ions, but hey, free textbook, I'm going to say that they are incorrect there. All right, okay, that concludes the section on acid-base reactions from part 4.2 of our book. I hope you found the video helpful. There are a lot of questions where you can practice writing these acid-base reactions, and I'd encourage you to have a look at a couple of those.